it is next generation. So what is it about? Well, it's 10 times faster on disk, first of all. This is what happens whenever you watch the other guy fail, and you're like, and then you fix it. You're like, ah! It's actually like the third generation of what MapReduce, the progression of MapReduce. So they've learned some things and fixed some things, so this is what Spark brings. 10 times faster on disk, 100 times faster in memory, and that's one of the things that's pretty critical. You can do in-memory workloads. It works out of the box on elastic MapReduce, and we get these fault-tolerant distributed sets. And that fault tolerance is really interesting now, because then we get into this situation where I was talking about Cassandra, how you can have failures in your system. I've had people lose servers all over the place. I don't know how many of you use Amazon Web Services, but hey, you know what they did for you as a service? They rebooted your server. Yeah. We're going to reboot your servers. No, you can't stop it. They did that to everybody. Netflix had a great blog. They lost 218 Cassandra servers. 0 downtime. Now, if I'm running MapReduce on that, I'm going to start losing data there too. So you need something that can keep up with that failure rate. Because let's face it, Amazon's not going to give you reliable infrastructure. It'll be cheap, but it won't be reliable.
One question.
Yes.
What is the usual time to write to disk? So you said it's asynchronous.
On what part?
So when you write something,
yes.
First in memory, you get the result immediately.
It should take about 10 microseconds to write to disk. A write is a very fast operation to disk. Typical 95th percentile is in the 10s to 100 microseconds. It's reading which causes trouble because you have seek time. Yeah. So back to the fault tolerance, we want to have a system that's fault tolerant along with our infrastructure. So we do batch, we do streaming, and this is really what Spark is about, is just kind of the next generation of things. And when you look at this faster, 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 less code is another part of this. I don't know if you've ever written MapReduce code, but that can get ugly. So what are the components? You have your Spark core, which is really the elements that you need to do this kind of massive parallel computing, and that's really what it is. And then the libraries that sit on top of it. I'm going to talk about Spark Streaming today, a little bit about MLib, which is the MLib, the machine learning, and a little bit about Spark SQL, but GraphX, there's a graph component as well. All of these sit on top of the core for Spark. And just recently they did this petabyte sort, 23 minutes to sort a petabyte of data. I'm totally shocked. Who has a petabyte of data? Google has this thing called GDEP, I think it's called. It's all the news articles ever in the world from like 1900, and it's like a 50 terabyte database. So what's a petabyte besides my Facebook stuff? It's amazing, but they did a petabyte sort in 23 minutes. The thing you need to know, if you learn one thing tonight about Spark, is learn RDD. Now, those of you that have done infrastructure probably know what an RRD is. You'll say that about 1,000 times before you say RDD. So an RDD is a resilient distributed data set. And this is the fundamental part of Spark. This is the data, this is where you manipulate data. So whenever you ask for a row of data or data out of a file, you push it into an RDD. And that RDD is essentially a Scala collection. So think of what you can do with a collection. You can sort it, you can count it, you can filter it. It's a very fast in-memory operation. So RDDs are that fundamental atom of what makes Spark work. They are immutable. So as with immutable data sets, you can pass them around and you get good concurrency. They're partitioned, meaning that we look at where the data is pulling from and it can spread it out across the cluster, so massively parallel and completely reusable. If you need to change out an RDD for one another, there you go, no problem. So with an RDD, you get all these neat functions, where we used to just do map and reduce. Now we're doing filters and group by, join, and we can do other actions. Here's these are the transformations, and then these are the action itself. Collect is the big one because that's when you say, okay, make it all happen. That's like the go button. So here's a very simple word count that's done in, I'm going to say one line, but it's actually more than one line. This is very fluent. But most of these examples are in Scala, so I don't know if Scala's like a language a lot of people get, but this is pretty easy to understand. I'm going to read a text file and create an RDD with that. That Spark context will create an RDD. I'll map it, I'll do a flat map, I'll split it, and then I'll bust it into pieces with, I'm going to map each one of these clean words into this map called word, and then I'm going to do reduce by the different words, I'll split up the words, and then I'm going to print out each and single word and the count for each word. Did that in one line.
Do you have adapter for Node.js?
For this?
Yeah.
No, you mean a driver for Node.js?
Yeah.
No. There's one for Python.
Okay.
Yeah. Node, I don't think would be very good for that. Node is a reactive language, much more than what you would expect with Scala. It's not just pure functional. I've never really been able to do anything like that with Node. It's great for making servers, terrible for CLI. So when we talk about creating these RDDs, here's a simple example. I'm going to parallelize this sequence. And so built into this parallel processing framework is this ability to look at the job and then figure out how to split it out across multiple nodes. Granted, this is a very simple workload, but think about if you have a petabyte of data. You probably want to split that up a little bit. And you can you can parallelize this entire collection into an RDD. And once it's an RDD, you can do things with it. You can suck in all these text files from this directory. You can pull it from HDFS. You can do sequence files. And those are all interesting because they use HDFS, which you probably might have if you have Hadoop. But I like this idea better, using Cassandra. Now, this was something that just happened. We didn't plan on this. About a year and a half ago, somebody did a talk at one of our summits, the Cassandra Summit, and said, you know what? I started using Spark on Cassandra, and I don't run Hadoop anymore with it. I just analyze my Cassandra data. Now, why is that even interesting? Well, now we get to do some fun and now analytics type workloads on Cassandra. So we can do server-side filtering. We can do joins now, unions. And we get that data locality awareness. Cassandra already, because you know how the partition key works now, boom, we already got the locality awareness. And we can just apply that to how Spark works, and I'll show you how. And we can do transformations and aggregations, which is not something that Cassandra does out of the box, but is a really important part of analyzing data. And when you combine it with what we do with time series, it's a great fit, because you collect a lot of data, you're going to have to aggregate it, you're going to have to use it. And so Spark on Cassandra was a really good fit. Now, we have open sourced the Spark Cassandra connector. It's not a driver. What a lot of people think what it is actually doing is it provides the translation layer. Cassandra stores data in a certain way. An RDD looks a certain way. Hey, this is kind of a good fit, because a row of Cassandra data can be an RDD. Now you can take a row of that Cassandra data and do things with it. Count, aggregate. And you can do that massively parallel. So that 1,000 node cluster, we test every day on 500 node clusters with Spark and Cassandra. So that massively parallel operation can be done pretty easily. So not only can we load data and transform it, we can write it back into Cassandra, which creates all kinds of interesting workflows now. Because we can transform our data and stick it back into Cassandra and use it in our applications. That's very interesting for application programmers, because now they can do interesting workloads with Spark, but then have that fast access time with Cassandra. So the type conversions, if you love Scala, you'll love implicits. So it's all implemented in Scala, and so we also have a Java API. The data stacks and the Spark connector has not yet come out with a Python driver. Well, there will be one soon for Python. And those are really the three main languages supported by Spark, is Scala, Java, and Python. There are no Node, or Ruby, or any of the others. This is completely open source, of course. It's sitting on GitHub if you'd like to download it, and I'll have the links at the end. But then we get to do some really interesting things with Spark and Cassandra, because we get RDDs and we get streaming. I have examples. So how does this work? The Spark executor is actually a very small thing. So like a task tracker in Hadoop, where it's organizing and sending out jobs, the Spark executor sits on top of the Cassandra node itself. So if you have a 4-node Cassandra cluster, you run 4 nodes of Spark right on top of it, so it's locality aware. But then what's really interesting about the Spark executor, it's very small. It runs in its own JVM, but it's only a few hundred megabytes, very tiny. Whenever it gets a job, it forks out or spins out a new process to run that job, the child process. So the executor is just a very small, lightweight thing sitting on your server that can execute code. So whenever the Spark executor talks, it goes to the connector, which talks to our to the Java driver, which talks directly to Cassandra. So it's a very pure connection to Cassandra. So here's a very simple example of the connection to doing something. So when you connect to Spark, or you connect to Cassandra, you just give it the host, the local host, and you give your what your Spark master looks like, again, to the local host. You create a row, a Cassandra RDD, which is just a row of data from Cassandra, and it's this tweets table. And you can create a streaming context if you want here. Or you can just do a transformation. So in this case, we're doing a transformation on a stream of data from Twitter. And if you notice right here, we're doing word count in the stream, and we're pushing it right into a Cassandra table. These are the type of examples of things that are actually being done because you're interested. So as you're streaming data, like you're watching Twitter throughout things like hashtags and stuff like that, okay, well you can collect those and put those directly into a Cassandra table. There's a lot of social media companies that use Cassandra for just this thing. I don't know if you've heard of Gnip. They got bought by Twitter. Huge Cassandra cluster. They do this all day long. They're one of the fire hose people for Twitter. So, and it keeps up with that massive load of data. So let's go back to our weather station. So let's put this to real world. Now we have this weather station that's collecting data. It's great because we're putting it in a Cassandra cluster. What's bad is I want to put this badge on my website. And here's the problem. A daily high and low, which is a pretty normal thing you would expect on a website for weather, is what was the high and low for that day. And that's an aggregation problem, right? That's like, hey, I need to know all the temperatures, and I need to collect them. When you use Cassandra, that aggregation workload is not something that's natural to Cassandra. So what I'm going to do is I'm going to add a little Spark. So I create a new data model. I have this thing called a roll-up table. So I have this daily aggregate temperature, very similar. I have my weather station ID, year, month, day. But then I add two things, high and low temperature. Cool. Now that looks a lot like that raw data table for weather. But in this case, this is just a daily aggregate. So whenever I ask, hey, for Windsor, California, that's where I live, by the way, what was on July 1, 2014, what was the high and the low? I want to ask one time from the database and get that back in just a few milliseconds, because I'm going to display that on a mobile application or on a web page. And if you write mobile apps, you know your budget for time on the database is really small. So you need a fast query. You're not going to be able to run like a MapReduce job or something like that. So I'm going to store my data here. Think of this as like a materialized view. But how do I get that data in there? So I'm going to walk you through a real quick thing here. I'm actually going to run a Spark job over my raw weather data. So I'm going to set up my connection to my database. So here's, I'm going to connect to the Cassandra node, and then I'm going to connect to my local weather. Here's my connector, and I set my key space, which is like where all my tables live. And now I can start